Today, I'm going to show you one additional thing, but everything I'm going to talk about today, you know. And because of that, congratulations, you know Maxwell's equations. So if I would say what are the most beautiful equations in physics, I would say E equals mc squared when we talk about special relativity, F equals ma from Newtonian mechanics, and then for E and M, it's these four equations right here. They're called Maxwell's equations for E and M, and with them, you can solve almost every classical physics, classical E and M problem. So they're very wonderful, and they also will explain to you why light you can think of as an electromagnetic wave, or well, we'll get to that. So let's begin. Maxwell's equations. Okay, so the definition, I found this online, I'll just say it to you. Maxwell's equations are the mathematical equations representing the electric field and the magnetic field, and how one affects the other, and how they affected by charge and current, and how the charge and current affect fields. Okay, so that's a lot to take in. Let's think about what we know already. So we know that charged particles, you know, if you're dealing with a charged particle creates an electric field. We know that. So a charged particle creates an electric field. And you know that if a charged particle is moving with a velocity v, then it will create a magnetic field, right? So this moving charge, let's see here. So if the current's going this way, it'll create like a magnetic field sort of like this, going in, going out, like that. So a moving charge will create a magnetic field. That's something we know. We also know that if you take a charge that's moving, and put it in the presence of a magnetic field, the magnetic field causes a force to push on the moving charge perpendicular. So we use the right-hand rule. If the velocity is this way, the magnetic field's into the page, it's going to feel a force going up as soon as it enters. So a magnetic field causes a force on a moving charge perpendicular to its direction. Something we know already. We also know this, that if you have an electric field, some electric field here, and you put a charge here, electric field causes the force to push against the charge. And in this situation, the charge doesn't have to be moving. So regardless of whether or not the charge is moving or not, if you put it in the presence of an electric field, it's going to feel a push. The charge is going to feel a push or a pull, whatever you want. A force is what we could say. And then finally, the last thing that I didn't really talk so much about was this. If you have a charge and it's moving, you know, v, but there's also an acceleration. It's not only moving, it's accelerating. Accelerating charges create an electromagnetic wave, okay? So they create electromagnetic radiation. So if this charge is not only moving, but it's accelerating, then it's going to emit an electromagnetic wave. That's something new. We haven't talked about that yet. And when we're done with all our math and all this other stuff, I'll get to why that is. Okay? So everything that I've shown you so far, I have talked about. I've reviewed it. So you should know all of that. Let's put it into mathematical equations, though. So all of this stuff was pictures and whatever, you know, we get that. Let's talk about the actual equations that are involved. And the funny thing is that when I learned this the first time, I had no idea. But I think, I don't want to take too much credit. I think I've given you enough that you should be able to understand almost all of these, except for the last one, which we'll talk about. The first one is easy. The first of Maxwell's equations is Gauss's law. For electric fields. And so that's written as the enclosed integral of E dA equals, and this is a dot product here, that's going to be actually pretty useful to know, is equal to the charge enclosed divided by epsilon naught. So if you've got a charge here and you put it in a blanket, you know that it's all going to go out. There's going to be a number of field lines that are going out but not coming in. This is going to be actually really useful when we talk about the divergence theorem. But that's Gauss's law. So you cover in a blanket, you can figure out how much charge is enclosed. All right, great. Everybody's happy. We're good. The second equation, which I don't think I've ever actually mentioned in words, I mean, I've mentioned it, but I've never actually written it down. And that is Gauss's law. G-A-U. Whoops, I can't even spell today. G-A-U-S-S, Gauss's law for B. And so what's Gauss's law for B? Well, we write it the same way. B dot dA, just like that. And the enclosed magnetic field is equal to 0. That is the second equation. Sometimes they put a question mark here because we don't fully know, but we could write it like this. Now, what does this imply? It means that if you have a magnet, right, north, south, and you put a Gaussian shell around it, then there's going to be field lines going out, but the number of field lines going out are going to equal the number of field lines going in. And therefore, the net flux is equal to 0. Okay? So, and this is equal to the flux. Magnetic, electric. And this is going to equal the flux magnetic. So the number of field lines going in is equal to the number of field lines going out. So the flux is equal to 0. And what that's really telling, if you want a really intimate relationship with this equation here, that's a terrible way to phrase this, but if you want a very deeper understanding of this, you have to understand that magnets always come in pairs. There is no such thing as a magnetic monopole. You're not going to have a single north here, and then if you put a Gaussian shell, all the magnetic field lines are going to go out. So magnets don't create magnetic monopoles. That's the real beauty of this part of the equation. Okay? So look at that. Maxwell's equations, there's 4 equations in total. We got 2 of them done already, and you should know these 2. Now the other 2, you know as well, because we've been doing it. The next equation is Faraday's law of induction. Whoa, which color should I use? Let's use this one. So we got Faraday. Is there 2 R's? Faraday? Yeah, I think so. Faraday's law of induction. Okay, so what is Faraday's law of induction? The first 2, we talked about the flux. These next 2 equations, we're going to be talking about the change in the flux. So the Faraday's law of induction is written like this. E dot ds is equal to negative the change in the magnetic flux over dt. And if you don't know what this means right here, it means voltage. So voltage, I could write it like that. Voltage induced is equal to this term right there. Okay? But this is how we write it. So a change in the flux will create a electric field. Let's take a quick picture of what we have. So if you've got a ring loop here and you've got magnetic field that's going this way, B, right? There's magnetic field there. If you change the flux, meaning the number of field lines or whatever, the angle, the field strength that's going through this loop right here, if you change that, you will create a current. And the current will move according to the right-hand rule. Now, this right-hand rule that I'm doing, look at my fingers. What they're doing is that they're curling, and they tell me the direction of the current. And this is actually going to be important when we talk about the mathematics of this. There's a word that we use, Zoe wrote it earlier. It says that it's with the curl. And that's actually what this is. This is going to be a curling equation right here. So when we write the differential version of this, all we're doing right now is the integral version of Maxwell's equations. When we talk about the differential versions, then this idea of current going around is a curling vector, which we can talk about later. So if you change the flux, in this case we're changing B, if you change the flux, you will get an electric field, and the electric field is what's causing the current to go around. If you don't have an electric field, you're not going to have current. Okay? So that's that. The last equation, so far, you know this, you know this, you know this. These are three equations we've done. The last equation is something you also know, and it's this one right here. What color? Oh, yeah, we're using this. He's one of my favorite guys, Ampere, because I'll tell you why he's one of my favorite guys. He's got like two fancy E's in his name. I think one's like that and one's like that, or something like that. I don't know. Amperes Law. And Amperes Law is kind of the opposite of this. Just like you had one for electric field and one for magnetic field, you also have this for electric field, and then you have this one for magnetic field, which is written exactly the same way. B dot ds, okay? B dot ds. Is it dot ds? Yeah, sure, why not? And that's going to equal, now wait a minute, here we had the change in the magnetic flux. If you remember Amperes Law says that when you do this, it's equal to mu naught I enclosed. Just like Gauss's law was equal to Q enclosed over epsilon naught, we get this. No, this is actually not Amperes Law full equation. This is only a part of Amperes Law. So now I'm going to give you the full equation of Amperes Law because we want it to be symmetrical to these. Like this idea was symmetrical to this. This idea has to be symmetrical to this. Changing the magnetic flux creates an electric field. So over here, we're not seeing that. We have to add an additional term. And we're going to say, we're going to add to that this right here. I'm going to write it two different ways, okay? So the first way is like this. Mu naught epsilon naught, the partial derivative, d dt, of the integral of E dA, E times dA. Okay, so that's one way of writing it. Now wait a minute. Wait a minute. Just hold on. I know you're probably going to tune out after seeing this, but just give me 1 second. Look at this. This is E times dA. We have E times dA over here, and we said that that was equal to the flux. So if I take a derivative of that, if I take the derivative of the flux, this is the flux times the derivative, we get the change in the electric flux. So Amperes law is really, let's see if I could write it down a little bit better. B dot ds, just like we did before, is equal to mu naught I enclosed plus mu naught, how are we going to write this? Yeah, sure, why not? Mu naught epsilon naught. And instead of this, I'm going to call it the change in the electric flux divided by dt. Now we have our change in flux. So when we did a loop, when we did this curling vector thing that we're going to be talking about later, we get a change in the flux. Or we could say the change in the flux creates an electric field. Over here, what we're saying is a change in the electric flux will create a magnetic field. And let me just show you that really quickly. So I'm going to erase this term. We don't need this one anymore. We're just going to look at this bottom one right here. So Amperes law was that if you have current I going this way, then there's going to be a magnetic field that goes around it, B. That was Amperes law. Look at this. Current going this way, and you produce a magnetic field. Now the current is actually an electric field. So you have electric field here, electric field here. And moving charges will create a magnetic field. This is also curling. The one we had before for Faraday's law was kind of the opposite of this. What we had there was a current going around I, and going through that was this generated magnetic field, B. So this and this are the exact opposite. The magnetic field is going around, the current's going that way, whereas over here, it's the current that's going around and the magnetic field's going perpendicular. I don't know if you've ever thought of that. You know, you might have thought of these as separate things, but look at that. Look at the beauty of this. This is symmetry right here. It's doing the exact opposite. And it says that in our equations here. Changing the magnetic field will do the electric field. Changing the electric flux will create a magnetic flux. Okay? And this really is defined as the curl. So with those four equations, let's take a look here. Equation 1, equation 2, equation 3, and equation 4. If you understood those, congratulations. You know a lot more than many first-year physics major students. This is Maxwell's equations. And you, hopefully, if you understood all of these, now know them. There's another way to write them using what we call the differential versions of Maxwell's equations. This is the integral version of the Maxwell equations. The reason why we use the integral version is because it's easier to explain, which is why we don't talk about the differential form in Physics C, but we're in Physics C. So on Wednesday, we will talk about the differential forms. But for now, if you understood this, this, and this, you can do pretty much almost all of E&M. Like this is it. Maxwell took all those ideas that we've talked about for the second semester. He put them into these four equations. And if you can use these four equations, you can solve pretty much anything. That's why they're called Maxwell's equations. They're so beautiful. They just work, and they work really well. Now, from this, we can also deduce, because these things are going to be doing the opposite, as one thing goes down, the other thing goes up. What you'll notice later on is that by changing one will affect the other. So if you change the magnetic flux, it will affect the electric flux, and it'll go back and forth. And you'll get these sinusoidal waves that are perpendicular to each other that we call electromagnetic radiation. Okay, and that's where we get the light from as well. And with this, we used to think that light had to be an electromagnetic wave. So for a really long time, once Maxwell came up with these ideas, physicists thought that that was it. We're good, man. We can solve all of E&M, everything with waves and light. Not so much. There's a few things that you can't solve with these kinds of equations, and that's what led us to modern physics, which is quantum mechanics and all that stuff. So a few things I just want to note. You can solve a lot of things with Maxwell's equations, but you can't, it doesn't explain why you have things like the photoelectric effect or black body radiation or Compton scattering, and I think there's maybe one more. But everything else, this thing is good. So we can think of light as a wave, and that's kind of where we're going to proceed with this. We can think of light as a wave, and maybe if you stick around and we keep going, I'll explain all those modern physics terms as well. Whoa. Okay. So let's keep going here. I have to show you where this term comes from right here. I haven't explained this term right here. It's called the displacement current, and we'll get to that in just a second. Let me just quickly, just a few more things that I want to say. Now, if you want to make me a proud Physics C teacher, you have to let me know that you understood those equations. That would imply to me that I was able to teach it to you. So really quickly, let's talk about the speed of light. This is just a review now. So for the speed of light, we have two equations, the electric field and the magnetic field, okay? Thank you. Thank you. I'm grateful for that. So the speed of light. Let's talk about the electric field and the magnetic field, and then the speed of light. And this is just quickly a review. If you have a particle here, plus q, and it's some distance r away, where you've got this point P here, and you want to know what the electric field is at point P, well, that's pretty easy. It's just the electric field for a point charge. That's Q over 4 pi epsilon naught r squared in the r hat direction, if we're going to call it a vector. And similarly, instead of a charge, let's say you had moving charge going straight up. So this is the current I, and then we have a point P here. And we want to know what the magnetic field at that point P is. Then we can use Amperes Law, and we can say that the magnetic field is equal to mu naught times I over 2 pi times r, where this distance is also r. So the electric field gives you the permeativity of free space, and the magnetic field will generate the permeability of free space. And I'm not going to rederive it again, but just to remind you, Maxwell looked at these ideas and he said, you know what? There's got to be something between epsilon naught and mu naught. And it turns out that, I'm going to erase this. It turns out that C, that constant we love so much, is equal to the square root of mu naught times epsilon naught. And if you plug that into your calculator, that's going to be the square root of 4 pi times 10 to the power minus 7. That's mu naught. And epsilon naught is 8.86, I think. 8.85 times 10 to the power minus 12. So when you plug this into your calculator, you will get 2.998 times 10 to the power 8 meters per second, which is the speed of light, roughly. So that's the last thing I want to say about Maxwell's equations there. All right. Finally, we can talk about that new thing that I was mentioning before, this idea of displacement current. So just remember this as we go along here, okay? changing the flux magnetic resulted in electric field, roughly speaking. Now we're going to be looking at Amperes Law, where we change the electric flux, and we should be able to generate a magnetic field. Okay, that's the idea, the basic idea. It's not the right equation here, but that's the idea. Changing this will produce a magnetic field. Changing this will produce an electric field. So let's quickly write down Amperes Law one more time. Amperes Law, the full equation is B dot ds is equal to, I'm going to write it as mu naught epsilon naught, the change in the flux electric dt, plus mu naught I enclosed. And what we're after is the understanding of this part right here. Okay, we already know that. We already know that if you put a line there, you can use the enclosed thing. We've talked about that before. Who cares about this part? This is the part we're interested in. And to explain that, what I'm going to do is I'm going to talk about something that we've already discussed before, which is parallel plate capacitors. So you've got two parallel plates. One is positively charged, one is negatively charged. They're going to be a distance d apart, and they're going to produce an electric field. You know, it goes from the positive to the negative, like that. And the voltage, there's going to be a voltage across them, delta V. So we've got delta V, we've got the distance here, d, and what else? We also know the area. So let's just write down everything that's going to be given here. I'll write over here. Given delta V is equal to 100 volts. Keep it simple. The distance between the two plates is equal to 1 millimeter. And the cross-sectional area, is going to be 0.01 meter. All right. So that's what we're given here. And we're going to try to extrapolate everything that we can from this parallel plate capacitor here. What'll happen is this. You could think of like this electric field going through a specific area that we can call a Gaussian, not a Gaussian, an Amperian loop. So instead of current, maybe there's a wire connected here and here, and you can make a loop there. We're going to make our Amperian loop through the electric field itself. All right, that's kind of the idea that we're going to be going with. But before we do that, let's see some of the things that we can solve for. Well, I'm going to move that over here. I'm going to go over here. So one thing we can solve for is the capacitance for parallel plate. The capacitance is given by epsilon naught times the area divided by the distance between them. So if we solve for capacitance, it's going to equal, what is it going to equal? 10 epsilon naught. We'll leave it in terms of epsilon naught. So 10 times epsilon naught, and then this is in meters. So 10 times epsilon naught in meters. That is the capacitance. Something else we can solve for is the charge Q, which is equal to C times delta V. And that will equal, well, C is 10 epsilon naught, and delta V is equal to 100. So we will end up with 8.85 times 10 to the power minus 9 coulombs. So that's Q. What else can we solve for? We can solve for the magnitude of the electric field. The magnitude of the electric field is given by the change in the voltage divided by the distance. Remember, it's the slope of the voltage divided by the distance is the electric field. There's a negative sign here, but we're looking at the absolute value of the electric field. And so that will equal, when you take 100 divided by the distance, which was 1 millimeter, you will end up with 100,000 volts per meter. Volts per meter. And I'll explain why I'm going through all of these at the end. Finally, we have E. We can find the flux. The flux, electric, is equal to the electric field times the cross-sectional area. So the electric field is given by this term right here. The cross-sectional area is over here. So when you multiply these two together, you will get 1,000 voltmeter. Yeah. Okay, so that's the flux right now. Now, if it's just the flux and there's no change, then we shouldn't get any current. What we're going to do, though, is change the flux as a function of time. So we're going to say, let the flux, we're going to say, what are we going to do? We're going to change the voltage. So if we change the voltage, we're going to be changing the overall flux. So we're going to say, let delta V equal 100 go to delta V equal 0 in 10 seconds. Okay? So we're going to let the voltage go from 100 volts to 0 volts in 10 seconds. How can you do that? Maybe you remove the battery, and so the voltage here is going to decrease, 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 and then die down. So we're going to let the voltage go from 100 volts to 0 volts in 10 seconds. So what do we end up with? Well, if we're going to look at the current here, the current is going to be going from this much to 0. The current, I, is going to be the final, the initial minus final, it doesn't matter. We're just looking at what the current's going to be. So it'll be 8.85 times 10 to the power minus 9 minus 0, all divided by 10 seconds. And we get that the current is equal to, just bring this one up. So it's going to be 8.85 times 10 to the power minus 10 amperes. So that's my current right there. All right. Hopefully we're good. If the voltage goes to 0, then the current through, well, let me say again. If the voltage is going from 100 to 0 in 10 seconds, the current has to go from this much charge to 0 in 10 seconds as well. So our current is going to equal 8.85 times 10 to the power minus 10 amps. Why am I talking about this current right here? Let me show you something really interesting. I hope it's interesting. If I take this, if I take epsilon naught and I multiply it by the change in the electric flux divided by time, if I do this, right? If I take epsilon naught and multiply it by the change in the flux here, let's see what I get. So the flux is going to go from 1,000 volts per meter to 0 in 10 seconds. And we're going to multiply that by epsilon naught. So if I do this, I get 100. 100 times epsilon naught is equal to 8.85 times 10 to the power minus 10. 8.85 times 10 to the power minus 10, which is exactly the same as our current right here. I is equal to 8.85 times 10 to the power minus 10. So if I take the change in the flux and multiply it by epsilon naught, I get the same result as if I just look at the current. So what we call this thing in the blue right here, is an imaginary current. There's no real current there, but it's changing a flux here. Sorry, not the blue thing. Changing the electric field here will create this imaginary current, and the imaginary current will create a magnetic field between the two plates. And it's going to be the same value if this was a wire here. The magnetic field outside is going to be the same as the magnetic field here, which is going to be the same as the magnetic field there. And what we call this term right here is called the displacement current. So ID is equal to epsilon naught, the change in the electric flux, divided by dt. And ID stands for the displacement current. So even if you're not in a wire between two parallel plates, there's no wire connecting them. Even if you're between them, you get this imaginary current that's going in some direction. Stokes for Stokes' theorem. Okay. So even if you don't have a wire connecting here to here, you're still producing a magnetic field around this electric field line right here. And that is called the displacement current. So let's write Amperes Law one more time, the way I like to write it. But the way Amperes Law is really written is with this term. I like to write it like this. So let's go back to Amperes Law. The integral of B dot ds is equal to mu naught epsilon naught, the change in the magnetic flux, electric flux dt, plus mu naught I enclosed. So that's Amperes Law the way Gauss's law writes it. But we just established this. All of this is I displacement. So we could write it like this. Mu naught I displacement plus mu naught I enclosed. And we could do it one more time and just write it as mu naught I displacement plus I enclosed. And that is another way. This is another way of writing that right there. But as for good practice, it's probably better to just write it this way. But know that this term right here, epsilon naught times a change in the flux, magnetic, a change in electric flux will create a current, and a current will produce a magnetic field. So changing the flux, electric creates a current, and the current creates a magnetic field. We already knew that from Amperes Law before. A current carrying wire creates a magnetic field, but what we didn't know was that changing the flux can also create a current. It's an imaginary current, which can create a magnetic flux. And that is Amperes Law the complete way. So I think that's all I wanted to say for today. Now you have in your arsenal of physics all of Maxwell's equations. I don't know if the other teachers are going to go that far. Well, I know they didn't go that far. So, oh my God. Akane, you just got that joke? Wow. So that's it for Maxwell's equations today.